Just going to use this as a classic example for something you've seen before, but something we want to pay a little more attention to, okay? We can use the sine rule in this question, right? And it's easy to see because you look at the information you've got, two sides and two angles, or you've got one angle and you want to find the other, okay? So wherever you've got that pairing happening, that's what makes it a good candidate for the sine rule. Now, because of the way it's phrased and what we're after, which version of the sine rule do we want? Because there's two, right? I mean, they're reciprocals of each other. They're very similar. Okay, so because I want an angle, right? Instead of writing A on sine A, I'm going to write it the other way around. Just so I have my unknown on the numerator, that's the minimum number of steps. So, in this triangle, I can say sine theta on the opposite side equals sine the other angle and its opposite side. No big deal. By the way, excuse me, it's really important to write the rule like that. You may immediately see, oh, I can just chuck that 9 over there, and it's still mathematically true, but it's not the sine rule, right? If you want to be super ultra sure, you can write the sine rule over here, but that doesn't get any marks. I almost never see it, and the form is so unmistakable. It's so distinct that it's kind of like, okay, as soon as I see that, I know what you're talking about. Okay? So I'll just rephrase it a little bit. Sine 45 is an exact angle, so that's 1 on root 2. So this is going to become 9 on 7 root 2. Okay. And then you reach for your calculator, and this is obviously going to be some messy thing. Let's just go to the nearest degree. Like, I don't care about accuracy at the moment all that much. Just so that I can get a ballpark for this thing. Yeah, cool. 65.38 something something. So let's call it 65 to the nearest degree. Okay. Now you look at this and you think, well, that looks good to me. That works, okay? And sure enough, it does. But as you know, right, the sine rule has this thing called the ambiguous case. The ambiguous case. And this is one of them, right? Can someone explain to me, what is the ambiguous case? Yeah, Vincent. Okay, very good. So this angle here, theta equals 65 degrees, is only one possible option. The other option would be, what would the other option be?
180 minus
115 to the nearest degree. Okay, now the question is why? Why is it that there's this extra option?
Sorry, sir.
That's okay. This other thing that the angle could be, okay? And the way I'm going to illustrate it is to appeal back to something you've been looking at for a little while now, which is the graph, okay? So, when you've got the graph of y equals sine x, okay, it looks like this. Now, this value over here, 9 on 7 root 2, I didn't calculate it, but what is it actually equal to? Like that number. It should be some weirdo decimal.
1 point something.
1 point something something?
0.9.
0.9. Yeah, 1 point something something would be a bit of a concern since it would be outside the range of, but anyway, okay. So we got I've got 0.909. Roughly. Okay? So where is that on my graph? Okay? Because what does this statement mean? It's where does sine theta, which is this, right? Bless you. When does it equal to 0.909, etc.? Okay, so here's one. Right up the top here. So 0.909 is quite close to the top, right? I'll just pop it there. 9 on 7 root 2. Should say y equals. Okay, so being that that's where the line goes to, you can see there is not just one solution, right? There's another one. There it is. 65 and 115, okay? So because of the nature of what sine looks like, right? When you pop in at this line here into your calculator, theta equals sine, and then you use sine to the power minus 1, etc., right? Or that's what it looks like it says. It's only going to give you the first angle. It's only going to give you the first angle. I mean, it could give you an infinite number of solutions, but it just has to pick one, okay? So it picks this one, and it leaves it up to you to work out, okay, there's another option, okay? Now, we said this is the ambiguous case, but it's not always ambiguous. There are two ways that you can know that sometimes, actually, it's not one or the other. It has to be one versus the other, or yeah, it has to be one specific one. Can someone give me an example? When do you know, yes, it can't be both angles, I'm locked into one of the choices? Nikita.
When side B equals 1.
Say that again.
Sorry, when side B equals 1.
Okay, sure. So if I had a triangle, right, and I went through all of this, and I got sine theta equals 1, there's only one spot in this domain, right up here, bam, right, where sine theta is equal to 1, namely 90 degrees, okay? So, fair enough, you're not going to get an ambiguous case there because, well, I suppose you are, but it just so happens that both cases are the same. There's 90 and there's 180 minus 90. So there you go, there's one case. Another suggestion, Brendan.
When the obtuse angle is lot plus the already given angle as to more than 180.
Okay, good. So sorry, let me just write these in because there are three now, right? So case 1 is where sine theta equals 1, so theta is equal to 90, this is the only case. Case 2 is where, when you check these out, right, you have a look at the bigger angle and it doesn't fit in the triangle you've been given. For instance, if we just adjusted this a little bit, 115. Suppose it wouldn't work in this triangle, but I could manufacture one, where that angle, if I add it to the obtuse version, it breaks the triangle because, well, these two are 185 degrees, and I have a third angle which has to fit in there somewhere, right? So unless that's a negative angle, I'm in some trouble, okay? This triangle doesn't exist, okay? So case 2 is where the obtuse angle is too large. Where the obtuse angle, if you add it into all the other things you know, it exceeds the angle sum of a triangle, okay? So they're the easiest ones to spot. There's a trickier one, case 3. It's a bit more subtle. Yeah, Reynard.
Do they say like the angles obtuse?
Okay, so they may actually say to you, they might provide you like an actual statement that says the angle must be obtuse or the angle must be acute. So there might be some kind of domain restriction. I suppose I'd kind of include that kind of on this, right? Minsu, do you want to give one more suggestion? Say it again.
All the sides are given.
All the...
Sides are given.
Oh, okay, sure. Yeah, all right. So if I have another side, like this one down here, okay, that gives you more information, right? So think about it this way. You know when we say for triangle proofs, right, for congruence, if I have a triangle like this, I don't know, 3, 6, 8, okay, and then I draw another triangle, like, what's that orientation? 3, 6, 8, okay? These triangles and all of their angles must be exactly the same, right? Because there's no other way that you can fit those three sides together such that you'll get different triangles, okay? Now what this is saying over here is that with this amount of information, I can make two triangles, right? I can actually draw it. Like this angle here won't look like this, it'll actually be going off at another angle like that, right? So therefore, if I know what all three sides are, then I know exactly what the angle must be. So it's not like it can be this or the other, okay? And there's one more actual case I'm thinking of. I'm just going to write it down for you. When you have the sides, okay, see, I'm going to get rid of this extra triangle over here. I don't know if you noticed this, when we were looking at the reason why a tangent is perpendicular to the radius, at the point of contact around a circle, okay, we noticed that when you have pairs of sides, right, a bigger angle means that the side that's opposite it, like these two, right, a bigger angle means that the side must be bigger. That kind of makes sense, doesn't it? Like literally, as you take the two sides of it, I had another one, where'd it go? You want to see it? I have a yellow ruler. It's disappeared.
On the floor.
Where?
Oh,
here it is.
There you
Oh, you still look.
Okay, so here we go. I don't have three arms, and I don't have three rulers either, so you just have to imagine, right? So here are two sides, and the third side is joining up the top here, like in between these two bits at the top, okay? So if I have a very, very small angle between these two sides, right, then the side that's opposite that really tiny angle at the bottom, okay, sorry, I should hold it up so you can see. The side that's opposite it, the side at the top, will be really small, right? And as I increase the size of the angle, the side also gets bigger. Does that make sense? Right? So in the same way, you can argue that if this angle is opposite a big side, right? And this angle is opposite a smaller side, okay? This angle must be bigger than this angle. Does that make sense? Let me say it again, okay? Because this side is bigger than this side, the angle that's facing it must match, right? So big side, big angle, smaller side, smaller angle, okay? So if what you get here, right? So this can actually take you both ways. So case 3 is comparing relative side lengths. So this can go one of both ways, right? Suppose when you, excuse me, do sine theta, right? If this angle over here ends up being smaller than this one, something has gone wrong, right? Can you see that? Like suppose I calculated, theta over here is like 31 degrees, okay? But then you have a small side, a small angle opposite a big side, right? And a big angle opposite a small side. It doesn't match up, okay? Or it can go vice versa. If I have this angle over here, and then I look at the obtuse angle, right? But the original angle's got a bigger side facing it, okay? It won't make sense. Big side, big angle, small side, smaller angle. It just so happens in this case that both work. Can you see that? Both work. Either of these options are bigger than what you've got here, so either of these options will work because they're opposite the bigger side, okay? So you've got all these different ways that you can determine what should the angle actually be. Should it be both? Is it truly ambiguous? Or do you have some other information that locks you into it being one or the other?